Okay, I think we can get started tonight. I hope everybody can hear me, both those here and afar. So my name is Peter Trapp. I'm Dean of the College of Science. I'm delighted to welcome you to this installment of Frontiers of Science. Got a fabulous lecture lined up from Kurt McMullen from Harvard. But before we get into the lecture, I want to say a few words about the lecture series itself. As many of you know, it's the longest running lecture series on campus. It was started in 1968 by Pete Gibbs. He was then the chair of the physics department. And in the intervening years, there's been a great number of distinguished lectures given. Pete passed away about a year and a half ago, and I had occasion to talk to his sons about the Frontiers lecture series. And I said, you know, what was it like in the late 60s and the 70s, attracting all these distinguished visitors to Salt Lake City? Because Salt Lake City was a different place back then. It really was the Wild West, I think, in many ways. And they said, well, the formula is really very simple. You offered to take them skiing a couple days at Alta, and that was pull enough to get these distinguished visitors to come and give the series. And I don't think the formula's changed much in the intervening years. We're still doing it. And I was delighted to see that we had our first kind of real storm last week, so we didn't embarrass ourselves on that front either. So I'm going to turn things over to my friend and colleague, Ken Bromberg, who's going to give Kurt a proper introduction, and I hope you enjoyed tonight's lecture. So you can.
Hello. Yeah, so I'm happy to have Kurt McMullen. I wrote a few notes here, so hope I can read them. From Harvard University, who's going to give our Frontiers of Science lecture. I have to take my glasses off to read what I wrote. On negatively curved crystals. So Kurt has won many awards and prizes, including the Fields Medal, the Guggenheim Fellowship, the Salem Prize. He's a member of the National Academy of Science and the American Academy of Arts and Sciences. He's well known for his work in hyperbolic geometry and dynamics, and I think we will see some of that today. But I also think he's well known for his enthusiasm for discussing mathematics equally with his fellow Fields medalists as with a first-year graduate student or one of his former students, and I can personally attest to two of those three categories. He's also well known for his skills as an expositor, both in writing and lecturing, and with that, I will let us all experience that. And please take it away.
Okay, thank you so much.
Do you need to put this
Oh yes, I guess I need to also be on the web, so let me connect up to that as well. Okay, so it's a real honor to be here again, speaking on the Frontiers of Science, this long-running lecture series, and also it's a real pleasure to be back in Salt Lake City and so close to Alta, as was previously described. I know that mathematics is not a typical topic for a science lecture, and well, first, I really appreciate people coming, and secondly, I'm going to start by asking maybe a somewhat atypical question to situate ourselves in this discussion I'm going to present. So my first question is going to be, where is mathematics? So mathematics exists in our universe at many different scales, so, ranging from the cosmological scale, where we have galaxies and the remnants of the Big Bang, to the subatomic scale, where the rules of quantum field theory dominate. And at those extreme scales, mathematics appears to provide the natural language for expressing the fundamental laws of nature. But mathematics also exists at the mesoscale of life on Earth, where DNA and evolution and human culture and universities exist in all their complexity. And at this scale, mathematics exists as a social and cultural phenomenon. So let me just pause for a moment to reflect on that fact. So first, mathematics is perhaps one of mankind's greatest cultural achievements. It's the result of centuries of thought and discovery mediated by the miracle of language, which allows knowledge and the accumulated culture to be passed on from generation to generation. And the fact that our culture of mathematics exists within a physical universe governed by mathematics is kind of interesting and paradoxical. Let me give you a kind of cartoon illustration of that. So here's a very simple model for a sort of toy caricature of a physical universe where there's a bunch of cells in the plane, and they change according to a very simple rule. This is called Conway's game of life. If there's too many blue cells in one spot, then they die off. But if there's an empty spot that touches just 3 cells, a new cell is born. So imagine we have a vast world filled with a kind of random configuration of these dots. And then somehow, as you start to look at it farther and farther back, after a long period of time, it almost seems like something purposeful is going on. And then you maybe zoom out to a larger scale, and you see something that looks like a small molecular engine inside of a prototype for a cell. And then you zoom out an enormous scale larger, and you see the rules for the game of life being written in English. Well, that's a kind of toy model for this circular way in which our mathematical culture has emerged from the laws of nature. Okay, so those are 3 scales where mathematics resides in the physical universe, but classically there's another place that mathematics is found. It's on a sort of metaphysical level, divorced from the physical world and even perhaps divorced from humanity itself. And this idea was put forth by Plato, who posited that mathematics is the discussion of ideals. The Platonic ideals are, for example, the perfect renderings of triangles or cubes or of the famous Platonic solids, which I've drawn here and which were known to Euclid. There are exactly 5 very symmetric solid shapes: the tetrahedron, the cube, the dodecahedron, and their duals, the octahedron and the icosahedron. And somehow in our world, we don't see absolutely perfect cubes, but we see some sort of shadows, imperfect shadows of them. But the Platonic idea of mathematics is that there is a world where Euclid's axioms are exactly correct, and within that world, one finds these pristine mathematical objects. Now, classically, these ideal shapes were also associated to the elements, the 4 elements that were thought to exist at the time: earth, fire, air, and water. For example, fire is this very pointy shape, which is why it hurts to put your finger in a candle, and water is this very round thing, which is why it flows so easily. Cubes stack, so they're earth. But there was no natural element to correspond to the dodecahedron, so it was said to correspond to quintessence, which just means the 5th element. So I think it's interesting to ask, as long as we're thinking about the interaction between mathematics and the universe, whether or not nature knows about the dodecahedron. And I think there was a certain amount of time when people thought the answer was no. So in fact, nature does know about the dodecahedron in the sense that there is an amazing molecule made out of pure carbon. The molecule is called Buckminster Fullerene. Its chemical symbol is C60 because it takes 60 carbon atoms to make just one of these molecules. So it's in a way much more exotic than, say, a diamond. And this molecule was not initially found in nature. It was synthesized by 3 chemists in the 1980s who 10 years later won the Nobel Prize for their work. And it was named Buckminster Fullerene after the famous architect who promoted the idea of the geodesic dome, like the American Pavilion at Expo 67. But later, further investigation showed that these fullerenes might occur if you had carbon that was somehow left by itself under the right conditions for a long period of time. So there's a paper published which claimed that fullerenes occur in ancient Chinese ink sticks. But later it turned out that, in fact, carbon-60 does exist in nature. In fact, it can be found in soot if one looks hard enough. And in fact, here's a picture of the American Pavilion being turned into Buckminster Fullerene when it caught on fire a few years after Expo. So what about some other examples showing nature knows about these more complicated Platonic solids? Well, this might seem topical. This is not COVID, but it is the protein capsule for a virus. And it's not quite the dodecahedron, it's the 20-phase solid called the icosahedron. So there's 20 kind of triangular shapes which piece together to form the protein capsule that contains the RNA genome of this virus. And there's a reason why this virus likes using the icosahedron, which is that to have the DNA code for one of these triangles takes only 1/20th the room of having the DNA code for the whole icosahedron, which has 20 faces. So when this virus invades a cell, the RNA that's injected starts to produce these triangles, and the triangles self-assemble to form these icosahedra, which then render additional spread of the infection. Another interaction I like very much between the natural world and the Platonic solids was proposed by Kepler. So Kepler intervened between Copernicus and Galileo. He was one of the first defenders of the Copernican system with the sun at the center of the universe. And Kepler, working from the data of Tycho Brahe, had a pretty good idea of what the radii are for the orbits of the planets. And he was looking at the ratios of radii and trying to see how there might be some sort of harmony in the heavens. And what he noticed is that if you make a sphere that goes through the orbit of Saturn and another sphere that goes through the orbit of Jupiter, you can just fit a cube between their two orbits. And then you can just fit a tetrahedron between the orbit of Jupiter and Mars and all the way down to Mercury. And so in this way, he proposed that the Platonic solids were built into the architecture of the solar system. And this not only provided a beautiful explanation for the size of the planetary orbits, but it explained why there are only 6 planets. So let's see what happened in the later evolution of our thinking about these Platonic solids. So the next kind of revolutionary idea, which is not so remarkable at first blush, but becomes more so as we dig into it deeper, was put forth by Felix Klein in the late 1800s. So what Klein noticed is a couple of things. First, he noticed that the dodecahedron, which is made from 12 pentagons, when we make that as a Platonic solid, it has corners. But you could also make these pentagons on the surface of a perfectly round sphere. And then they would fit together completely smoothly and seamlessly. And so he observed that these 5 Platonic solids really corresponded to positively curved surfaces. That's what k greater than 0 means here, positive curvature, like the round sphere. And he then proposed that we shouldn't stop at 5, but why not go on to 6? What can you do with hexagons? Well, of course, you can make a honeycomb tiling of the plane out of hexagons. And why didn't Plato or Euclid observe this? It's because this shape is completely flat, whereas this one's positively curved, so it can wrap up and give a closed solid. But this one is incompatible with, you can't make a sphere out of hexagons of this shape. But even more remarkably, he showed that if you took regular 7-gons, you could piece those together to give this sort of crystalline tiling of a negatively curved space. And that's going to be my main focus today, is on what these negatively curved spaces look like and how they're related to sort of crystalline periodic patterns and tilings. Now, this insight of Klein's is one that we can easily discover ourselves, I hope. So if you've assembled something during the talk, can you please bring it forward? So I had some helpers. Thank you, Ken. Thanks. Thank you. I'll fix this one. Oh, perfect. You have done it anyway. Awesome. And now,
Very flat.
that's okay. It's supposed to be. And that's okay. Awesome. Okay. That's great. Thank you. Okay, so here's a very simple experiment that you can do with triangles. If you have triangles that fit together nicely, is you can write down the numbers 3, 4, 5, 6, and 7, and then you can take triangles and try to, let's see if I can find some loose ones here, try to just piece them together. So there's 2 are coming together at a vertex, and then you can put in another one and make it so that 3 come together at a vertex. And then you get a shape that's almost already the tetrahedron. If you put on the base, you then have a shape with just 4 triangles, and at every point 3 come together at a vertex. So the number 3 knows about the tetrahedron. And similarly, the number 4 knows about the octahedron. And so what we see is these Platonic solids they just emerge naturally from the numbers 3, 4, and 5. So here is the Christmas ornament, or icosahedron. This was what the virus was based on, and they weren't amazing discoveries by the secret school of Pythagoreans. They were just assembled by people in the audience working with triangles. And now what Klein observed was that we can just keep going. So why not put together 6 triangles coming together at a vertex? And you get, of course, this flat piece of material that you might use to build something other than one of these solids, but you can't wrap it up to make it into a sphere-like object. And then this is the most interesting one and the trickiest to build. So this is 7 triangles coming together at every vertex. And you see, what you get is a surface that really does not like to live in 3-dimensional space. It's buckling everywhere. And the reason it's buckling is that this surface is negatively curved. This surface is positively curved. It closes up nicely. This is flat. And this one is negatively curved. And we can keep going. We don't have to stop at 7. We can go on to 8 and so on. And these tilings are finite for 3, 4, and 5. They give these closed solids. And then we get a tiling of the plane when we do 6. And then what about for 7? Well, it turns out that when you put these 7 triangles together at a vertex, you get something that looks sort of like the Euclidean plane, but it has a very different shape to it. It's what's called the hyperbolic plane. So let me I will, as we go along, try to explain how to think about this picture. In fact, that's the main goal of my talk, is to help you understand how to think about and visualize negative curvature in the same way that we can easily visualize spheres and positive curvature. Okay, so to continue, I need to say a little bit about the mathematical classification of surfaces. So the most familiar surface is, of course, a round sphere. And think of this as a kind of a stretchy, blobby surface. You know, the Earth is not perfectly round. It's a little bit pear-shaped, certainly like an oblate spheroid. But there are many surfaces that are topologically spheres. A football, for example, would qualify for me as being a sphere shape. But there are more complicated shapes. There's, for example, this donut shape here, which is fundamentally different from the sphere. And the reason it's fundamentally different is you can start at one point here, and you can go to the opposite side in 2 fundamentally different ways. Go from here or go from here. And those flights are not similar to one another. Whereas here, sort of all the flights that go from one point to another, you can deform one path to another path. And once you've made a donut, you might as well make a pretzel. and in between something with two handles. And it turns out that the closed surfaces are very easy to classify, and this kind of almost intuitively obvious. Surfaces are classified by the number of holes or handles they have. The sphere has no handles. The torus is sort of something with one handle. This object has two handles, this has three, and so on. Then the number of handles is called the genus of the surface. Okay, so were Plato and Euclid arrested at the number 5? It's because they really wanted to make spheres. There was a conceptual barrier. You needed to think outside the box to consider using polygons not to build spheres, but to build shapes like this, or maybe even like this. So let's see how that works. So this is a mathematical result that was known around 1900, although it took a while for mathematicians to even figure out how to say this statement. And the statement is that every surface can be geometrically tiled. And, intuitively it means something like what we're looking at here, except the tilings now will allow for surfaces of higher genus. So for example, a square can be used to build a donut. And the way you do this is you imagine taking 4 squares like this, and you roll up this square piece of paper to form a cylinder, and then you have to do something that requires a little distortion. You bend the two ends of the cylinder around until they're joined, and then you get a donut here. This is sort of a top view of a donut. And you can see this donut is made out of squares. I mean, at least these are distorted squares, but they come together at 90-degree angles, and they have 4 vertices. So they're pretty much like ordinary squares. And there's another way to think about this relationship between the torus and the square, which is that there's a sort of crystal pattern in the plane. You can tile the plane by many copies of a single square, so it becomes a kind of periodic motif. And then you can take this plane and wrap it up to form a torus by rolling it up into first an infinitely long piece of paper and then bending the paper around so it closes. So think of this as some sort of crystal. It's a very kind of mundane-looking crystal, like a cross-section of a salt crystal. What I want to discuss today are more exotic crystals, and the first one I want to really discuss in detail is this one. This is what I call a negatively curved crystal. So let's look at what's going on this side of the picture. In the center of the picture, there's a pentagon. That is, there's a 5-sided figure. But this pentagon has 90-degree angles. That's bizarre, right? Only a square or a rectangle should have 90-degree angles. Well, you might object that the sides of this pentagon are not straight. And the response is, well, this pentagon is not a pentagon in the ordinary flat plane that we're used to. It's living in what's called the hyperbolic plane, a plane of negative curvature. And in this plane, these apparently curved lines are actually straight. And in fact, this 5-sided figure here is exactly congruent to this one in the center. Moreover, as you look towards the edge of this picture, you see smaller and smaller 5-sided shapes. Well, in fact, they're not smaller. They're all identical in shape to this one here. It's just that as they recede towards the horizon, they appear to be smaller as a matter of perspective. So it takes a kind of a while to get your mind into this setting, but once you kind of start to accept the idea that there could be a geometry that's different from the most conventional one we're used to, you come to understand that there could be 90-degree pentagons. And moreover, if you had such a pentagon, you could use it to build a surface of genus 2, a surface with 2 handles. In fact, here you see, again, a distorted pentagon, but it's a 5-sided figure. And if the angles are 90 degrees, it fits perfectly well with this adjacent pentagon and with the 2 above. So in 2 dimensions, pentagons can be used to form crystals and to build surfaces of higher genus. By the way, if you've ever tried to tile a bathroom floor using pentagons, you know that you don't get very far. I mean, they don't fit together very well. The remarkable thing is that in negative curvature, you can buy a set of pentagon tiles and they fit together perfectly. And you don't have to stop with pentagons. Here's, in genus 3, you can use 24 seven-sided figures to make a surface with 3 handles. And here's what your tiling or crystal would look like. And here, this has been commemorated. It's well known to mathematicians, and it's commemorated by this sculpture due to Ferguson that sits outside the Math Science Research Institute in Berkeley, California. And so on. You don't have to stop with genus 3. There's an infinite sequence of similar tilings that are worthy successors to the 5 Platonic solids. The only difference is that they require that you change the topology of your surface from a sphere like this to these more complicated shapes. Okay, so somehow tiling surfaces, there's a beautiful harmonious story. What happens if we go to dimension 3? After all, we live in dimension 3. This should be the most interesting place to look for crystals and patterns. Well, it's quite different. So in contrast to the case of surfaces, which are ordered by their genus, the world of 3 manifolds resembles an evolutionary tree with phyla and species whose intricate variations admit, at best, a partial ordering by various measures of complexity. So this picture is metaphorical. I'd like to give you some actual images of 3-dimensional spaces so you can get an idea of how rich 3-dimensional geometry is. The problem is that it's easy for us to stand outside of a surface because we have 1 extra dimension available, but it's hard for us to stand outside of 3-dimensional spaces since we are in 3 dimensions to start out with. So instead, I'm going to show you another way of looking at 3-dimensional spaces, which is that 3-dimensional spaces are very closely related to knots. So this is a picture of a knotted strand of mustard suspended in space. And you should think of it as being like a complicated sort of higher dimensional torus in the sense that there's many paths to get from one point to another. You can go from here to here going above the knot, but you can also go behind here, down here, up here, under this strand, and come back out here. There's a multitude of ways to wrap around this single complicated shape. And that illustrates the richness of the topology of 3-dimensional space. Now, the classification of knots has a long and difficult history. So Lord Kelvin, who you know from absolute zero, proposed that atoms are knotted vortices of ether. Now, don't ask me what ether is, but his idea was that perhaps hydrogen is a very simple knot. The ether is spinning around maybe like a figure 8, and then uranium is a very complicated knot, and when there's chemical interactions, the knots somehow link each other and so on. And it was, impossible to disprove this theory, so people ran with it based on his reputation. And in fact, Tate and Little undertook to make a table of all the knots up to 10 crossings. So to describe a knot, one typically draws a picture of the knot in the plane, like I did, like you can see here, and there's undercrossings and overcrossings, and that describes the knot. And in 1899, they were able to put together this table, and they found 249 knots with up to 10 crossings. Just a small selection from the table is shown here. Now, I should say, it's not too hard to write down all the possible knots that have 10 crossings. What's really hard is to tell whether or not you accidentally wrote down the same knot twice. You might have a picture of a knot here and a picture of a knot here, and if you pick this one up, jiggle it around, twist some strands, put it down, it's actually the same knot as the one you're viewing. You're just viewing the same knot from a different angle. So the hard part was to make sure there are no repetitions in this classification. And this gives you some idea of the richness and complexity of shapes in 3-dimensional space. So for example, the previous knot might be in this table somewhere. Can you find it? It's quite tricky because you might be viewing it from the wrong angle. Now, in 1967, John Conway, the guy who invented the game of life I showed earlier, found a very efficient notation for describing knots, and with it, he redid the 10-year work of Tate and Little in a couple of days. And in fact, he was so good at it that he then extended it to all knots with 11 crossings. So quite a tour de force. Both tables were wrong. There's a pair of knots that look very different, but which are actually the same, and they were discovered in 1974 by Ken Perko, a New York lawyer who was also an amateur mathematician. So the problem of studying knots and classifying them is really quite complicated and rich. So for generations, it looked like there was no good organizing principle for the theory of knots, let alone the theory of all three-dimensional spaces. Well, that changed in the past several decades. So in the 1980s, Bill Thurston made a very bold conjecture called the geometrization conjecture. I'm going to say it in a slightly non-technical way. And I should say that some of the great experts on negative curvature are here in the audience and in the math department at Utah. So they know a white lie is being slipped past at the moment. But roughly speaking, what Thurston conjectured was that all three-dimensional spaces can be geometrically tiled, just as we were able to tile all the surfaces in some geometric way. And this was finally proved by Gregory Perelman in 2003. This statement that all three-dimensional spaces can be geometrically tiled is really revolutionary. It's probably one of the biggest advances in mathematics in, say, the past 50 years. But what does it mean? Well, it's not too hard to get started on what this might mean. So these tilings that we discussed before have natural generalizations. The tiling of the plane by squares can be generalized to tiling flat space by cubes. And similarly, cubes really are related to crystals. Sodium chloride has atoms which stack in this shape, and if you don't disturb the pattern and you let the solidification take place, the precipitation out of solution take place very gradually, you can see these facets at a mesoscale as actual salt crystals. So that's one of the motifs or tilings that exist in three-dimensional space. But it turns out that most of the tilings of interest will not be flat tilings. Like the case of donuts with two or more handles, in 3 dimensions, the most important kind of tilings come not from flat space, but from negatively curved space. So let me give you a glimpse of what negatively curved space looks like. So, we may have heard that Einstein predicted that gravity curves space and so on, but it's very hard to imagine what it means for the space in front of us to be warped. So let me illustrate that with a picture. So here is a picture of a 3-dimensional negatively curved crystal. So let's just examine this picture for a moment, and let's think of it, to start out with, as just sort of a piece of architecture. So what we see are a bunch of beams with maybe octagonal cross sections. And if you focus your attention near a place where 3 of these beams come together, it looks like something that ordinary construction in Euclidean space could carry out. You just see 3 posts coming together orthogonal to one another. So if you look at this picture just at a small scale, it looks very similar to the world that we're familiar with. But how is it different? Well, notice that these 2 beams here are meeting at 90-degree angles. And so are these 2 beams. And so are these 2 beams, and these 2, and these 2. So in this picture, there is a right-angled pentagon. Not a right-angled square, but a pentagon. And that shows that this space is, in fact, negatively curved. Also, our favorite solid, the dodecahedron, is the fundamental chamber for this crystal. Just as a salt crystal is made out of cubes, the region bounded by 12 of these pentagons forms a single room in this tiling of negatively curved three-dimensional space. And the remarkable statement of Thurston's is that every three-dimensional space can somehow be built out of this kind of crystalline pattern. It has a unique and rigid architecture to it. So, by the way, if you make a small error when you're trying to build this space, it doesn't work at all. These structures are extremely rigid. They cannot be deformed, and they provide thereby a signature for three-dimensional spaces, a sort of architectural plan. Now, just to give you an idea of the contrast between flat space and negatively curved space, let me remind you that Amazon is constantly shipping objects in cubical or rectangular boxes, and the reason is these stack well in our space. But in a negatively curved space, they could use dodecahedra to ship items, because dodecahedra, at least of just the right size, they stack beautifully in negatively curved spaces. They can form the facets of crystals that fit together with no clashes at their vertices. Well, I'd like to give you just a small hint of Perlman's contribution to this breakthrough in mathematics and our understanding of three-dimensional space. And this is just going to be a hint. This is the most complicated equation I'm going to write down today. There's a way to take a sort of flabby three-dimensional space that you don't understand and turn the points in this space into sort of independent agents, like, different companies in an entire country, which, by Adam Smith's unseen hand, are all working for their own individual benefit, and yet somehow cooperate to advance the GDP and the primacy of the United States on the world scale. So this differential equation does something similar. Namely, the points of our space start evolving as independent agents. And over time, they start to reveal the underlying structure of the space. They first figure out sort of how it's connected together, and then once they determine how it should be connected together, they start to straighten it out and turn it from just a topological space into a space with a geometric structure, like this perfectly round circle that's emerging here. So that's a hint of how this curvature evolution equation, first investigated by Hamilton in this setting, led to this deep understanding of three-dimensional spaces. And to give you an idea of how useful and powerful this method is, I should point out that in practice, when people study three-dimensional spaces, they don't use this equation. They use some more ad hoc methods. And these ad hoc methods are completely practical. So in fact, before Perlman proved his theorem, Thurston already showed that all knots give rise to tilings in negatively curved spaces. And therefore, whenever you're presented with a knot, you can find, by some method, a blueprint for the knot. And this blueprint, by the rigidity I mentioned earlier, completely determines the knot, and it's uniquely determined by the knot. So if you want to test if two knots are the same, you just find their blueprints and see if they look identical. And with this new tool in hand, 3 authors in 1998 were able to classify the first 1,701,936 knots up to 16 crosses, and they did it in 2 different ways, and they got exactly the same answer. So knot theory has gone from the stage where people accidentally find the same knot twice and it sits in the tables for 100 years, to where we can now reliably classify these negatively curved spaces on a large scale. And the method is uses modern computing. By which I mean, in fact, this kind of advance ran when it was first worked out on many people might not know what this is. This was the early Macintosh computer, personal computer that you could carry around in a backpack. And in fact, that computer was already powerful enough to take as input a knot drawn with a mouse and find the blueprint for the knot. Okay, so that is the main advance in mathematical science and our understanding of three-dimensional space I wanted to convey today. Now, what else might we wonder about with this insight into hand? Well, one question might be this. Can we use our knowledge of three-dimensional space to describe geometric models for the universe, that is, at a cosmological scale? Can we guess the shape of the universe or make some proposals for what it should look like? So before we try to figure out what the universe as a whole looks like, let me ask a simple question. Is the universe infinite? Now, I know there's might be some controversy about how exactly to interpret this question, but since nobody knows, let me just take a poll in the audience. How many people think the universe is infinite? Okay. How many people think it is finite? Great. It's a tie. So I don't know the answer, but I would like to say the following, make a few comments on our previous attempts to address this kind of question. So some people have proposed that the Earth is square and flat. And it certainly looks like it at a small scale, especially if you live in a city that's laid out on a grid. But there's some problems when you try to describe the universe as being flat. For example, what do you do when you come to the edge? Sorry? So we've made some mistakes in the past. It looks at first blush like the Earth might be infinite, but in fact it wraps up and forms a sphere, which is an amazing thing, that it has no edge and yet it's finite. It's bounded. So that's one lesson to keep in mind when we contemplate what the size of the universe. Another lesson has to do with whether or not we really understand what large numbers are. How big is infinity? Well, let me take you back to the age of Archimedes, when this was the number system commonly used, Roman numerals, and the largest number you could write down was 3,999. So in those days, Archimedes wrote a famous treatise called the Sand Reckoner, in which he proposed a new number system that allowed him to construct numbers as big as 10,000, and in fact, he called that a myriad. He then developed a way to discuss myriads of myriads of myriads and so on, and he even estimated the number of grains of sand it would take to fill the universe. And let me just give you an idea of what people thought in those days. So the preface to his work reads, "There are some, King Gelon, who think the number of the sand is infinite in multitude." Imagine that, the number of grains of sand in the earth is infinite. And I mean by the sand not only that which exists about Syracuse and the rest of Sicily, but also that which is found in every region, whether inhabited or uninhabited. And again, there are some who, without regarding it as infinite, yet think that no number has been named which is great enough to exceed its magnitude. And then he goes on to explain a new system of numbers which is big enough to not only describe the number of grains of sand it would take to fill the earth, but the number of grains of sand to fill the universe. Now, it's interesting, what did he mean by the universe? Notice that Archimedes, his brilliant genius way ahead of his time, thought, of course, the universe is finite. And And in fact, he was working here some 1700 years before Copernicus with a heliocentric model for the universe, which is lost to us. There's no historical record of exactly how it worked. But the dimensions were roughly the following. There's the Earth, and then there's the orbit of the Earth. And at those days, they had a pretty good idea about how big both of those distances were. And then, of course, there's the planets. And then beyond the planets, there's the sphere of fixed stars. And the Greeks were able to tell that the stars were pretty far away using the fact that when the Earth went 6 months around the sun, the stars didn't shift very much. There wasn't an apparent parallax, at least given the instrumentation they had at the time. That showed that they were pretty big, and so they decided that the sphere of the fixed stars was in ratio to the orbit of the Earth, the same as the orbit of the Earth was to the Earth itself. And that was Archimedes' model for a finite universe. So I'm going to explore the conceit that the universe is finite. Let's suppose that the universe is finite, whatever that means. What might its shape be? What does our current understanding of three-dimensional space inform us as to some of the possibilities? So first, let me point out that one really doesn't know that much about the large-scale structure of space, and of course, one should really not distinguish space from time. One should discuss this as a four-dimensional problem, but let me, for the sake of argument, pretend that the universe is sort of a big three-dimensional space evolving in time, but possibly closing in on itself. Now, general relativity tells us that the matter and energy present in space warps the space itself. So the space could be positively curved, it could be flat, or it could be negatively curved. But if the distribution of matter and energy is approximately even throughout space, then it has constant curvature of one of these three types. So we might think, oh, constant curvature, maybe that greatly limits the possibilities for the shape of the universe. And what the advances I've just mentioned tell us is that it doesn't, because there's so many possibilities for a negatively curved universe. So let's work up to this a little bit. So let me start with positive curvature. How could our universe not have an edge and still be finite? Well, this was already understood in Dante's Divine Comedy. His picture of the entire universe formed what we now call a three-dimensional sphere. Namely, there was the surface of the Earth where we're living, and inside of the Earth were the concentric circles of hell. But what's not as well known is that these concentric circles of hell were mirrored by heavenly circles, celestial circles, that after you reached a certain point, they began to get smaller and smaller and smaller. The same way the circles on the inside of the Earth get smaller, and they finally nested down to a single luminous point called the empyrean. And so you could imagine that this is just like a sphere. You start at the South Pole, and the lines of latitude get longer and longer, and then they get shorter again, and then you're done. And you have a world with no edge, and still it's finite. So that turns out to be a plausible model for our universe. It could have constant positive curvature and simply be a three-dimensional sphere. Now, what if the universe is flat? Well, in that case, it might be like a sort of giant salt crystal. This is a very exaggerated version where the size of the crystal is like the size of the Earth. But the idea here is that it's like a video game. The universe would have the property that you start at the floor of the universe, and you start to go up, and when you go through the ceiling, you just come back through the floor. That's how you get around the idea of there being an edge. And if you go off the left wall, you come back in through the right wall. If you go back through the whiteboards, you re-enter from the back of the auditorium. And so you never encounter an edge to the universe. This universe is, again, finite. But notice what happens when you look around you. the universe appears to be infinite. Now, in other words, since there's no edge, as you look out, you just see more and more stuff, and it might take you a while to realize you're just seeing copies of the same world as the one you're on. Now, of course, if the scale were like this, we would realize it right away, but what if the scale is, say, 13 billion light years? It will take a long time before we can even see once around the rim of the universe. So this is a possible model for the universe if it were flat. And one thing I find particularly fascinating about this is it's just another version of this well-known sort of Hall of Mirrors effect, that to make the universe finite at the same time gives you an experience of infinity. So if you're in a room and there's two walls that are mirrors, it looks like you're in an infinite space. And similarly, our universe would not only feel infinite, but it would look infinite. We would see infinitely repeating patterns if, in fact, it wrapped in and formed a closed finite space. So there's a sort of paradox. A closed universe appears to be infinite from the inside. And we can build up this picture in a very simple way. Let me go down to a two-dimensional case, because it's harder to draw the three-dimensional one. So imagine you have a little square room with mirrors. First, the mirrors look to you like they go off to infinity. So let's just draw two infinite mirrors like this. And then, in addition to each of these mirrors, you see the reflection of one mirror through the other. So as you look out from your finite world, this one room, which is actually the only place there is to live, you apparently see many copies of these infinite walls, and copies of copies, and copies of copies, and so on, because of the repeated flexions, or because of wrapping around the universe over and over again in many directions. So what I'd like to do is give you a similar picture of what the universe would look like if it were negatively curved. A similar sort of Hall of Mirrors picture. And as a warm-up, let me look at this. This is an actual space in Tuscany. There's about 38,000 black and white tiles here. So notice that this is a flat space, and we see this infinite repetition of pattern. As before, the tiles get distorted and they get smaller and smaller at the distance, but we know intuitively that all these tiles are actually the same size. It's just perspective that makes them look smaller. That's one feature of this beautiful flat space. And the other feature I want to draw your attention to is the horizon. The horizon in a flat space looks like a straight line, as we're all familiar with looking out towards the edge of the ocean. What happens in a negatively curved space? So a negative curvature, again, you can have a sort of tiling pattern. So here, instead of square tiles, I've chosen Escher's Angels and Devils etching. And one should try to warm up to this picture by imagining that all of these figures, all of the bats and all of the angels are actually identical in size. And they only get smaller because they're receding towards the horizon. So this is, in fact, an entire world completely filled with competing angels and devils. That's one feature, that there's this perspective effect. As you go towards the horizon, they become tinier and tinier. But the second feature is that the horizon itself is a circle, unlike a straight line, which is what we see in our familiar Euclidean space. And that led me to propose the following experiment, which I put in the abstract for this talk. Namely, let's imagine that the universe is a knotted crystal. It's a finite world that's been warped into negative curvature by gravity. In this world, the thin walls of the crystals might cut out a pattern of circles visible in the sky at night. So there's walls all around us. We can't really see the walls, but we can see the outline of the walls. Each wall gives rise to a circle. What might the sky at night look like? So here's one possibility. So this is a picture with about 200,000 circles in it. And you'll notice it has a sort of periodic crystalline pattern. You see the same motifs over and over again, but it's not nearly as symmetric in an obvious way as the salt crystal tiling or the other flat pictures that we've seen. It has an incredible richness to it. Moreover, if the universe really were infinite, this picture would be completely black. We would see one of these horizons in every possible direction. So the only way I've been able to render this as something you can see is not by drawing all the circles, but just some very large number of them to try to illustrate what it would be like to live in a negatively curved universe. Okay, now where does this picture come from? Well, it's very simple. Let's think of this as maybe not a crystal, but as an apartment complex. So the apartment that you're living in is almost a triangular chimney. So here's the three walls of your apartment. You're living inside this triangle, but it goes up forever, sort of outside of the plane of projection. And then your apartment has a floor, and your floor is this circle here. So remember that a circle is the boundary of a plane. So think of this as something you can stand on, this floor that's at the bottom of your chimney. Okay, so that's one apartment. But you're in a housing complex with lots of neighbors. So what do the neighboring apartments look like? Well, they look like this. So here you see three more circular chimneys added, and their floors as well. And these adjacent chambers are added just by reflecting the chambers we started out with through these three lines. But we should also reflect through the floor. As we look down through the floor, we'll see some other apartments, so let's do that. And then we just continue generating more and more rooms until the entire universe is filled with copies of the original four-sided chamber. That's how these crystalline patterns actually appear and how they can be easily generated by a computational process from an almost trivial motif. Now, as I mentioned, in contrast to chemistry in the world that we know it, where there is only something like 200 possible crystal patterns, in negative curvature, there are infinitely many possible crystal patterns. And so there's infinitely many possible shapes for a negatively curved universe. And so in addition to this picture, there's pictures like this. There's a picture that lacks these sort of flower-like embellishments, but is based more on a pentagon. This has a negatively curved five-sided figure in it, and so on. There are infinitely many possibilities for the view of the sky at night. And these images are actually artifacts from an ongoing mathematical investigation that began many years ago, and which leads into present-day research. So let me just give you a glimpse of how and why these images were computed and why I'm bringing them to you today. So again, I'd like to go back in time now to Apollonius of Perga. This is, again, a classical result about circles. So suppose we draw a circle and then we draw two other tangent circles inside of it. Then there's a sort of triangular region left over. And what Apollonius showed is that there's a unique third circle that fits in here. It just touches this circle, and the outside circle. So there's a unique circle in this lower triangle that touches all three existing circles. It's there. But once we put this in, we create more triangles. And so we can put circles in there and iterate and so on. And eventually we get this shape called the Apollonian Gasket. So this shape was one of the earliest circle patterns that was investigated by mathematicians and that was generated by computer as something you could actually look at and share with other people. It was proved that this residual shape here, what's left over in black, has positive fractal dimension. All sorts of investigations have been made of this shape, even of late, related to number theory. But this shape was pretty easy to generate because we just start with 3 circles and then we just keep plugging away. And it was known for a long time that there were many other circle configurations that are beautiful and rigid and similar to these Apollonian configurations, but which cannot be so easily generated. And in 1995 or so, I wrote a computer program to generate one of them so I could finally see it. So think of this as sort of constructing a mathematical telescope. And this is the circle pattern that emerged. So what makes this pattern so fundamentally different from the Apollonian pattern? It's that these circles don't touch each other. So there's no simple way to generate new circles from the old circles. You have to just sort of find all the circles by some complicated recursive procedure. And it was a wonderful experience to see this image for the first time, which many people have discussed and known existed. This is sometimes called a Swiss cheese for obvious reasons. In fact, if you started with a round piece of cheese and then punched out all these white circles, you would be left with enough cheese to make another circle. Start all over again, punch out holes, and continue. I think that's how the Swiss make their profit. And this can be pictured, again, as a sort of celestial configuration. The picture that I've drawn here is a rather simple one. It corresponds to this kind of picture of the constellations you'll find in old books. But it can also be wrapped up onto the sphere to give it a more three-dimensional quality, which is similar to this kind of globe, celestial globe you can look at to describe the constellations as well. Here's a variant of that type of picture. It's in this world, everybody lives in identical apartments, but the apartments all have windows. And the windows look all the way out to infinite space. So there's identical apartments, and for some of them you can actually see off to infinity, and that creates holes in this space, which would otherwise be completely black. I decided after generating several of these pictures that for both scientific and social reasons, it would be interesting to try to create a tour of the images that can arise via these mathematical experiments. And this was partly because I became chairman of my department, and my department had no presence at all on the ground floor of the Science Center. At Harvard, people didn't even know what went on in the upper floors of the Science Center. And if you tell people that it's math, they walk out the door in the opposite direction. So I worked with a high-resolution, large-format printer that I got access to at MassArt and developed a poster exhibit of these mathematical illustrations, one of which I've brought in here so you can examine after the talk. And something really interesting emerged, which is that it's very different to draw a picture on a computer, to print it out on a letter-sized piece of paper, and to draw it 5 feet tall. There's just something unusual about the experience of seeing it at scale and being able to see it at many different scales. So I really invite you to come experience this. This is what my studio looked like. Eventually, this became a 9-panel exhibit in the atrium of the Science Center. And it kind of changed the way many people felt entering the Science Center. And there was no mention of mathematics, I should say, attached to these posters. Some people interpreted them as something having to do with X-ray crystallography, I heard. Maybe others seemed to be patterns for tapestries or bedspreads. Anyway, there were lots of interesting interpretations advanced, and I tried not to impede people's appreciation of these images with the preconception that they had to do with mathematics. So in the end, there were 9 images, and here's some of the ones, most of which we've glimpsed already. Here's 3 more somewhat exotic ones. And let me just say a few words revealing some hidden facts about the images that went on display. So for example, this image actually is just a tilted and recropped picture of this image. And this image looks a little bit more mundane, right? Because you can see this square tiling. So there is a square tiling implicit in this image, but it's been hidden to emphasize the more asymmetric features of this, this circle pattern. This image was called, I was approached by somebody who wanted to buy this image. They said it looked like a black hole. It turned out they were a chef at a very exclusive restaurant in Copenhagen, so we traded it instead for a reservation, which I haven't cashed in on yet. But this image is in fact almost the same as the previous image. There's actually a square motif in this image as well, and it's kind of hidden, but if you look carefully, you can see here's 4 circles that look kind of like a square, and here's 4 more circles that look kind of like a square, and this is sort of in the center of this square, and so on. So there's many different perspectives that one can adopt even for the same 3-dimensional space and the same kind of pattern. And in fact, these 2 images, which at first blush look kind of different, are almost the same image. In fact, this image is the same as this image, it just has fewer circles. So this is the apartment complex where there's no windows, and then I just opened up the windows to create this image. This is a sort of more biological looking shape, and again, it's a result of careful cropping. We started with something that was first drawn, in fact, in the 1980s. This picture, oddly enough, can be drawn by just taking your pen, putting it on the paper, and following a very complicated curve until it comes back and closes. And in the old days, that's exactly how it was drawn. In the modern version, we use the fact that there's a lot of circles here, and so we draw the circles instead of trying to trace out this long line. And by taking this picture, sort of turning it inside out, and then cropping the top part, we get the fern-like shape that I just showed you. And here's another, maybe final, rather complicated image, really seeming to lack a lot of symmetry. Also, here the circles have been drawn in color, so you can see them in order. They look a little bit like robotic arms reaching down from on high. But what I want to draw your attention to is how very complicated and fractal this picture looks along the edge of the boundary between the white and gray. I recently spoke about this image at ICERM in Providence, and in fact, it looks a lot like Providence River, as it, which flows from the ocean up to the city and the Institute. And secretly, it's actually a kind of seasonal object. There's a highly fractal snowflake, of which this is a cropped version. And if we just draw it in black and white, it looks like this. And the amazing thing about this picture is what we're looking at is actually an extremely furry white tree. And in fact, there's not a ball inside this tree. All these little inlets here, they actually come all the way down and touch the center here. And if I drew this picture at the ultimate possible resolution, the white would be completely gone. But the white is so hairy, it's so extremely fractal, that this object is essentially 2-dimensional. And when we render it, we see this very jagged shape. And again, this is a shape that was discovered in the 1970s by pure thought, and it was kind of just a fascinating task to try to view it under the telescope provided by the computer. So finally, let me just say just a few words about my favorite object, this original Swiss cheese. My current research concerns this kind of Swiss cheese object, and unfortunately, I can't understand the Apollonian Gasket. I can understand this object, but not the gasket, which is apparently simpler. And one of the remarkable things is that although these objects are so rigid, you can actually interpolate between them. So this object can be sort of continuously deformed to the Apollonian Gasket. There it is. and now we're coming back again. And I sort of understand everything that happens except exactly at the limit when we reach the gasket. So this is one of the frontiers of research here, is understanding the passage between these different apparently rigid shapes. Well, here's something I should mention in conclusion, which is that when I decided to make an exhibit of mathematical posters, I decided to limit myself in some way. There's so many mathematical images in the world, so one limitation was I decided to only draw circles. And I like that, so I want to point out some facts about circles in conclusion. A circle is an abstract object. It's like one of these Platonic ideals we've discussed. It's also a motif in nature. It's the shape of an iris. It's the shape of a wave spreading on a pond. It's a motif in technology. The wheel, the Large Hadron Collider, millions of other things are also circles. But maybe more profoundly, a circle is a reminder of the fact that you can have a universe which is finite and still has no edge. And as we have seen for me, and hopefully now for you, the circle can be thought of as a horizon that is infinitely far away. In fact, the circle would be the ideal symbol for infinity if it weren't already being used for zero. And it is also a gateway to the discussion of the multitude of crystalline patterns that appear now in the modern understanding of three-dimensional space. Let me thank you there. Ken.
Can you build a negatively curved quadrant?
Ooh. Yes, you can. So it's it's done in the way that okay. So one of the ways what Ken is talking about is having shapes which are not periodic crystals, but are okay. So there's a couple of answers to your question, but shapes that are not periodic crystals, but which have sort of a bounded number of motifs, but there's no overall symmetry. There's a kind of compositum of different molecules might be fitting together. Penrose tilings are examples of these in the plane. So I know how to make quasi-crystals via a simple procedure, which I'm sure you know already. Namely, if you scatter points in space more or less at random, and then declare each point to be the capital of the region that's closest to it, you get a dissection of space into a bunch of polyhedra. Usually no two of the polyhedra look at all like one another. But I think what you're asking is something more like kites and darts. That is, can I make a quasi-crystal where there's only finitely many polygons, but they fit together in an aperiodic way? And I don't know the answer to that. It's a great question. Yes?
I don't know, I'm just saying, like, what's the inside of the block? Inside the block of the roof, is that, I don't know, is there any mathematical connection there? So they're able to escalate inside the block.
I think that's a kind of fascinating question, is why different cultures are biased, for example, towards using the hexagon, or towards using a 7-sided shape, or towards using a 5-sided shape. So that's kind of beyond my pay grade to speculate on why that happens, but certainly there is, for example, the Alhambra in Arabic. That's right. There's an architectural object in Spain which is full of mosaics, and these mosaics exhibit all possible tiling patterns. There's 17 possible symmetries to a tiling pattern. So it's obvious that artisans have known the mathematics behind these periodic tilings long before we were able to formulate them precisely. Yeah. Yeah. Yeah, let's see if I can bring that up again. So let me see if I can go directly to that image. Hang on a second. Okay. Is this the image you were talking about? And here is the laser pointer. You press the button at the top, right there. There we go.
Okay, cool. So 1, 2, 3, 4, 5, 6.
Ah, yes. Okay, right.
Is that due to some of your choices?
No, so that's not a computer artifact. That is, in fact, that's one of the invariants of this picture, is that each of these round circles is surrounded by a certain prominent number of other circles. And in fact, it is exactly 7 that's in this image. And what happens in the movie is, in fact, you're not seeing a continuous sequence of frames. What happens is the number 7 is replaced by 8, 9, 10, all the way up to 30. And if it were to go up to 100, it would turn into the Apollonian packing. So that's not a computer artifact. It's actually the fundamental motif of this image, and it's the number that's changed to make the different frames. Good question. So please come up and have a look at the poster if you have a chance to before you leave. And thanks to everyone who participated in construction. Good. I went way over. Sorry about that.
Oh, I don't know what time it is, though.
Hey, that was fabulous. Thank
Oh.
you so much.
Oh, thank you for having me. Yeah, yeah.
Really wonderful.
Yeah, I'm sorry I went a little over, but I got carried away. So,
And we all
Always go over. Just speaker, we're desperate for it.
well, thank you